So in the previous module, we were talking about time and timer, about my wave and QPSK and BPSK. We're also going to talk about time here, but keep in mind that this is a different type of time. The time of my wave is the time at which my chipsets are communicating. Here, we're going to talk about stations sending frames to each other. And there are a few times that you need to be aware at the scale of 802.11. And those times are going to be the ones upon which everything else is built. So it's very important that you understand them. First, be aware that 802.11 doesn't like collisions. If you send a wave and anybody else at the same time sends a wave, basically nobody gets that wave, because these two waves get mixed to each other and we don't know who was sending what. So 802.11 uses a mechanism to avoid collisions as much as it's possible. And that system is called CSMA-CA, Carrier Sense Multiple Access with Collision Avoidance. You may have seen that name before, maybe in your CCNA Routing and Switching study, where we say that in Ethernet there is CSMA-CD, collision detection. So here we're not only going to detect and resend, we want to avoid collision if we can. And the way we do it is to have a few times. And the first time we use is what we call the slot time, which is pretty much going to be that tempo, not at which your chipset counts to decide if it's BPSK or QPSK, but at which your station as a whole counts to decide about what's happening in the cell. There are some variations of the slot time value depending on which sub-variation of 802.11 you're using, but it doesn't matter for now. What matters is that there is that slot time. And then there is also another time, which is called the short silence value, or short interframe space, SIFS. That is the smallest amount of time you can wait after a frame was heard before deciding that you want to send your frame yourself. And there is always a silence after a frame because, it's going to bounce on things, walls and maybe some faraway things, like a wall outside, and come back on you. So every time you send a frame, you want to always keep a small silence to let time for these echoes to dissipate before you send something else. So the shortest amount of time you can wait is that SIFS. And then there is this slot time. Everything else, all other times in the cell, are going to be derived from these two, the slot time and the SIFS. For example, in a normal communication, after somebody has sent, the next person to send is going to wait a time which we call the DIFS, distributed interframe space. And that DIFS is basically one SIFS plus two slot times. That DIFS will come back on it because it's very important as well. But this, for now, keep in mind that every time calculating the cell is going to be derived from a combination of SIFSs and slot times. Those values change again depending on the protocol, so here you have a few numbers. What matters is primarily what happens in G and A and AC, of course. And you see the SIFS is slightly different, but the slot time is the same for both. Do you need to know for the CCNA those numbers? Doesn't hurt if you do, because that allows you to understand that different stations with different protocols are going to implement a different view of the time at which the cell is running. So it's interesting to understand those differences. Let's suppose that you need to send a frame, your station. The first thing you're going to do is to wait a DIFS. And that's why DIFS is so important. Of course, you're going to listen to the air, and if somebody is sending, you're going to wait until there is no communication anymore. And then you wait that DIFS. Remember that DIFS is an SIFS plus two slots. So if at any time during the time you wait that DIFS, you hear transmission, then you stop counting, you wait for the transmission to be gone, and then until there is silence, you wait. And when there is silence, you wait a DIFS. And everything starts when there is an entire DIFS without communication, silence in the cell. Then what you do is that you don't want to send immediately, actually, because if everybody does the same, then everybody's going to wait a DIFS and send at the same time, and you have collisions. So that doesn't work. So what you're going to do is you're going to pick up a random number in a scale, and we'll come back on that scale in a minute. And you're going to pick up a random number in a certain range of numbers, pick that number, and count down from that number. And you wait. And you count down, of course, at the speed of a slot, right? And you wait that extra count before you decide to send. If at any time while you're counting down, you hear somebody send, well, you stop counting. You wait for that other frame to pass. And then when it's completed, you resume where you stop. You stopped at 18, okay, you stop there, and you continue 17, 16. And you do that every time you hear somebody else sending some traffic. You will see that people tell you, well, that's not exactly the way it works. In fact, the way it works is that when you have a frame that is being sent, at the beginning of the frame, there is something which we call the duration frame. Duration field in the frame is the duration of the frame, how long the frame is going to take to be sent. So if you read that value at the beginning of the frame, instead of keeping listening until the frame is gone, you know exactly how long you have to wait. So what you do is that you add that number to your countdown number, and then you go count down from the top, and you don't need to listen to the air because you know that as long as you're counting down to that 18 where you stop, somebody else is sending anyway. So, both ways describe the same principle anyway. You let that frame pass, and once it has passed, you resume a countdown from where you stop, maybe 18 and so on. Okay, now, there are a few words you need to be aware of. First of all, you're going to pick a number in a range. That range is called a contention window. That contention window may be varying in size depending on what happens, okay? So it's not a fixed range of numbers. It's fixed at the beginning, but if there are some collisions, it can change. But it's there, contention window. The number you pick in that range is the backoff timer. So that's the initial backoff timer you choose to wait, again, randomly, and to count down from. And then there is something else, which is the NAV, or network allocation vector. This is the time you wait. And of course, you understand that the backoff timer and the NAV are pretty much the same thing, at least at the beginning. As soon as there is somebody else sending, well, your backoff timer, you picked it, it's a number, it's there. But your NAV, you're going to change it because you have to wait longer now, because you have to let that other frame pass. So although NAV and backoff timer may be identical at the beginning, as soon as you have a busy cell, the network allocation vector is going to be finally larger than what the backoff timer was. Those three terms, you have to know them very well. They are very important for the mechanic of the transmission. Okay, so remember, you listen for DIFS. If the air is free for the entire DIFS, you're going to pick up a random number. Anytime the air is busy, you probably will have a situation where you have to wait. So at the end of the DIFS, even if the DIFS was a time during which there was a silence, you're going to pick up a number always, and you're going to wait. And of course, that contention window is going to be a range of number determined with slots. And the smallest possible number, of course, is going to be nothing, 0. And the largest possible range value is going to be the maximum number you can pick from. Again, it's random, right? So you can pick anything in between, and it's going to be called the contention window max value. So your contention window has a contention window minimum, which is 0, and a contention window max, which is the max number you can pick. And you pick up a random number in that range. So far, so good. And you count down from there. And you count down and you readjust your nav every time you detect that somebody else is sending. So that makes that your network allocation vector changes, but your backoff timer does not. Your contention window does not. You chose it and it's there, right? That's where you started from. Only the nav is changing at that point. Okay, now you reach 0, what happens? Well, if still nobody is sending, you're going to send your frame. And in your frame, as you saw, in the beginning of the frame, there is a field which is called the duration field, and you're going to tell the rest of the cell how long your communication is going to last. But remember, we cannot have two communications at the same time, which means that as you send, you cannot listen at the same time. So that means that if the medium is half duplex. If you send, you do not know if your frame is working out okay. You also do not know if the access point received it well, because maybe there are some RF conditions at the access point that makes that the AP didn't get it. So in every unicast frame that we send, we need to have a confirmation that the frame was received properly. That makes that every unicast frame in Wi-Fi is acknowledged. So you're going to send your frame, and the AP is going to receive it, and if the AP receives it well, it's going to tell you, acknowledgement, got it. This is where the SIFS comes into play. Because if you send your frame, then there is a silence. And then if anybody else who has a frame to send adjusts to wait a little bit and then send, then maybe that person would be sending a frame before the access point would have a chance to respond. And that would not be good because you would have sent a frame and you would never know if the AP got it or not. So when you send a frame, a unicast frame, the silence between that frame and the acknowledgement is going to be only an SIFS, not a DIFS and SIFS, a small one, a short one. And that makes sure, because the SIFS is smaller than the DIFS, that you're going to reply with the acknowledgement before anybody else has a chance to send their next frame. So you send your frame, silence SIFS, acknowledgement. If the acknowledgement is successfully received and you don't need to retry, etc., then there is this time, this DIFS, that the other station wait before they pick up the random timer and start counting. But you see, the SIFS is here to make sure that the app will get to you always before anybody else sends. SIFS, acknowledgement, DIFS, you need to know them all. This is in traditional 802.11. But in 2005, the IEEE decided to improve a little bit the system by creating what we call 802.11e, which is a QoS amendment that translated in the Wi-Fi Alliance into the Wireless Multimedia WMM certification that allows you to improve a little bit the way communication happens in the cell. And the reason why is because we said, well, how do you distinguish a voice frame, it's a real-time communication voice frame, from an FTP frame? And before 802.11e, there was no way. So it's not very practical, because we need to have a way to give more priority to the voice packets, because this is real time, than to these less critical packets than FTP is. So they designed a different system where basically you can create up to 4 access categories in your system, in your laptop, in your access point, and then you can classify traffic based on one of these 4 categories. AC is access category. And you see these categories on the side. You don't need to know them by heart, but it's useful, because if you continue in Wi-Fi, you'll see them all the time, because QoS is so important. Then, of course, you're going to drop packets or frames in each of these categories, and all these categories are going to count down in parallel. The trick is that the voice queue is going to pick up a number in a range that is much smaller than a video or best effort or guest. The more important the traffic, the smaller the window, the contention window from which you'll be picking up numbers. That's one thing. The second thing is that the DIFS also is going to vary in size. If you have a real-time application, your DIFS, which is not called DIFS, it's called arbitration interframe space, AIFS. It's going to be smaller than if the frame you have to send is background traffic. So not only do you count down from a small number, but you also guarantee that when you wait that silence, you're going to wait less if you're using a real-time application than if it's a less important application. Okay, so AIFS is the equivalent of DIFS when you use QoS. That's something you have to understand. And you also have to understand access categories, the fact that you can prioritize differently different types of traffic as you count down. The logic is the same, and you don't need to know those numbers by heart, but it's just to give you a view of what we have in AIFS. You see, for normal distributed coordination function, as we call it, DCF, which is a normal 802.11 without QoS, you have the values of CW mean and CW max. And then you have, for QoS, the AIFS value. And you see that for voice, the CW mean is 3, whereas for background, it's 15. And then for max, it's a lot higher if it's best effort background than if it's voice or video. The result is that those two queues, voice and video, are always going to weight less than the other queues. So they will have more chances of being sent and, of course, received than the others in a situation where there is congestion in the channel. Again, no need to know these numbers by heart for the exam, right? It's good if you do, but it's not necessary. What is important is that you understand the difference between these different numbers.